Today on Signal Galaxies Unlimited, we're going to be looking at building a basic spectral display and all that entails. To build my basic spectral display, I'm going to start with this basic flow graph. I'm going to be using a file source coming from a file that I recorded some time ago of part of the FM broadcast band. And the reason I'm doing that is that this will go faster due to the fact that I'm going to have to start and stop the flow graph many times. Whereas if I were to use a SDR such as this RTL SDR source, every time you hit play, it takes a while for it to initialize and come online. The only difference between this and this is the fact that I can't change the gain or the center frequency inside of the file source. Once it's recorded, it's done. But other than that, it should provide the same functionality, because once they come out of the RTL SDR source, samples are the same. The other thing that I'm going to be doing is I'm going to initially be coming out into this frequency sync and this time sync. What I intend to do is to turn this time sync into a frequency sync. And this is actually appropriate due to the fact that the first spectrum analyzers, such as this one, were actually based on using an oscilloscope display, and all they had was they had special modules which were plugged into it in order to turn that oscilloscope display into a spectral display. So I'm kind of going back to initial principles here. Starting with this, what I'm going to first do is we're going to be looking at creating, again, this frequency sync and this time sync. If I run this, I get this basic display. This is showing the time sync on the top, which is, think of it as an oscilloscope display, and then this is the frequency sync. And again, I'm going to turn this ultimately into this. The first thing that you're going to be doing when you're looking at creating a spectral display is we're going to be using the fast Fourier transform, the FFT. I have a lot more to say about that later. But the first thing that you have to understand is that the FFT is a block-based algorithm, meaning it does not operate on one sample at a time. It operates on a block or a set of samples at one time. Therefore, what we're going to first be doing is we're going to be adding a block called the stream to vector, this block right here, and we're going to we're going to make this into essentially our time record that's going to be fed into the FFT. Now, for the rest of this flow graph, this is going to drive a lot of the settings for the others. So I'm going to go ahead and also add in a variable block to set essentially our block size. And I'm going to use the most common letter, which is capital N, and I'm going to say that it is going to be, let's just say, 2048. I'm going to come in here. I'm going to say, strangely, you don't set the vector length, you set the number of items. I'm going to say capital N. Hello, hello, hello. Yes, hello, it's me, it's Gary again. I'm just going to put in here a quick correction that when you're looking at the stream to vector, all you're doing is you're just putting the samples into a block, a vector, an array, whatever. And then in order to see it in the time sync, I'm going to have to put in a vector to stream, and then that will display. Now, initially, all the stream to vector does is just put stuff into a block, and then the vector to stream puts it back into a stream, so you can't really see what it is doing. I'm just going to leave it at that, and then we're going to continue on with the rest of this video. Thank you. Enjoy the rest of the video. And to keep everything straight, I'm going to go ahead and set for my frequency sync and my time sync. I'm also going to set those to the same block size. So this, again, this stream to vector, that puts all of the samples into the one block. And again, the fast Fourier transform, the FFT, is a block-based algorithm. The next thing that I'm going to want to do is I'm going to want to do a window. Now, to understand the window, we need to take a step back for a second. The FFT is a block-based algorithm. What that means is it's going to take in a set of samples such as this here, and it's going to feed them into the FFT algorithm all at the same time. But you have to understand that from the perspective of the FFT, that doesn't really look so much like this as it does like this. Because of the fact that the FFT is sampled in both time and frequency. When you sample in one domain, that means that you create repetition or a repeating pattern in the other domain. If you remember from my video on talking about polyphase filters, I talked about Nyquist zones. Due to the fact that you are sampled in the time domain, that means that you create a repeating spectral pattern in the frequency domain. Hence, you have the various Nyquist zones, Nyquist zone 1, 2, 3, and 4, and so on. The same thing applies in the frequency domain to the time domain. So if I sample in the frequency domain, which the FFT is, I create this repeating pattern in the time domain. Hence, it's going to look something like this. And where we start getting the repetitions, in other words, the point where it starts repeating, if the end of the time record does not match the beginning of the time record, you wind up with these impulses. And impulses are noise. This is what creates the spectral leakage, the scalloping loss, and all of the issues of the FFT. Therefore, we're going to introduce a window. A window does nothing more here than add weights to the time domain such that it pushes the ends down to 0. And the point of that is that that will then take this time domain record and turn it from this into this. Notice now that the impulses are gone. We have a nice smooth transition from the end of one record to the beginning of where it repeats, and we don't wind up with the spectral leakage. We don't wind up with as bad a scalloping loss, although we still wind up with some. We'll talk about that later. But the point is that we have a nice smooth transition, which will then get rid of the worst effects of the spectral leakage. To add the window to our flow graph here, I'm going to first add in a variable block. And opening this up, I'm just going to change the ID to W. And then for the variable, the value, I'm going to say window.Blackman-Harris, all one word, and then in parentheses, capital N. So it's the same as the block size. So again, my ID is going to be W. My value is window.Blackman-Harris, and then in parentheses, capital N. And then in between, at the output of my stream to vector, I am going to add a multiply constant block. And the adjustments that I need to make here are I first set my constant to W, but then I also have to change the vector length to capital N. And notice it now says, okay, I'm happy, we're good to go. Looking at the output here, you can now see that I have adjusted it where the ends here of my time record are pushed to 0, which is exactly what I'm looking for. So now, again, remember that this is a repeating pattern, the way that the math works due to the fact that we've got a sampled spectrum. And so because I have a sampled spectrum, this should be thought of as a repeating pattern in the time domain, and you want the ends here to match up the end here. Before we add the FFT block into the flow graph, that's going to be the next step. I want to make certain that everyone understands precisely what the FFT is doing. In order to do that, what I'm going to do is I'm going to go ahead and take these various blocks running into the time sink. I'm going to disable them just so we're looking at the frequency sink. So looking at this particular display here, I'm going to take and I'm going to freeze this. I'm going to come in here. I'm going to add some markers. Yep, it's going to kind of make it look ugly, but I'm just going to zoom in on the center here. And I'm actually going to zoom in on the actual center. So when you're looking at these various values here, what you're seeing is, notice that there's lines connecting the dots. It's the dots that are actually the values. The lines are just a graphical thing that allows you, the user, to see the spectrum a little bit better. But if you were to actually look at the way that it's truly represented, this is how an FFT actually is represented. It's just a series of numbers. And when you look at these various values, all they are, again, is a number. And the display that's actually provided to you is showing you each one of the these frequency points. There's known as a frequency bin, and each one again represents a value that is the magnitude of a complex number created by the FFT. So again, each one of these is nothing more than a number representing the magnitude of the complex sample that is created by the FFT. Where does that complex sample come from? Let's get into that. This is the equation for the discrete Fourier transform. There really is no equation for the fast Fourier transform because, again, it's an algorithm. It really requires diagrams and pages of other equations to truly understand how the FFT does its magic. But again, all you're doing with the FFT is you are very efficiently implementing this equation here. Now, a lot of people will show you this equation and it looks daunting, looks complicated. There are lots of YouTube videos that try to go into how it works. And I'm going to give you my perspective of how I look at this particular equation. And that is, I look at it as a correlation, specifically a correlation of our signal, that's represented by this x of n here, times the complex exponential here. You have to understand, complex exponential is just another way of saying a cosine and a sine. The cosine represents the real part. The sine represents the imaginary part. And specifically, notice that there's a minus sign here. What that means is the sign is actually going to be negative sign. So in other words, I am taking my signal, I am multiplying it by a cosine and a sine, and then I am doing a sum of all of those values. That gets me one value for every value of m. This m here represents the number of the frequency bin for the output of the FFT. So this will actually represent a value that goes from 0 to n minus 1, just as the value of n does. That's because FFT will give you output in the same number of points that are in the input. So again, looking at it from the perspective of I'm going to take my signal, that's represented by x of n here, I'm going to multiply it by a cosine and a sine for each value of m. When you look at the actual spectral display itself, again, remember, it's just a series of numbers. We're going to start here on the left end. This is typically just called bin 0, meaning that it's the number refers to its frequency. 0 means it's DC, it actually doesn't have a frequency. So we're going to go from bin 0, bin 1, bin 2, and so on. And each one represents ultimately a complex number at the output of the FFT. The only one that does not is bin 0 because, again, it doesn't have a frequency, so it's not going to it's going to be a real only number. However, all the rest will represent complex numbers. And when you're looking at that what's being fed into it, what I'm going to use is I'm going to use this 2048 point example of a time record that we're going to talk about feeding into our FFT. And with this, what we're going to be looking at is for bin 0. Again, that's the DC component. All we need to do is take all these values, these 2048 values, add them together. That is the value for bin 0. All we're really doing with bin 0 is we are taking an average. So think of it that way. So again, bin 0, you're taking all the values of this time record, you're adding them together, creates essentially an average. That's what goes into bin 0. When we go into bin 1, that's the first one that actually has a frequency. Now we're talking a correlation. Well, now the question might be a correlation with what? We're talking about a correlation with a cosine and a negative sign. And it is a correlation of a cosine that is one complete cycle over those 2048 points. So I can literally plot out a cosine requiring 2048 points to complete one cycle. I am then going to take this one cycle and multiply it on a point-by-point basis with our time record. That will create this, which is our multiplied values. I'm now going to take the multiplied waveform here shown here on the bottom, and I'm going to add all of these points together. That will create the real value of a complex number that will occupy bin 1. For the imaginary component, let me come back to here. I am going to be using, where is it? This here, and this is our negative sine wave. But again, one cycle of a negative sine wave. If it was positive, it would be flipped upside down. But it's a negative, so it is one cycle of a negative sine wave. And again, I'm going to multiply this on a point-by-point basis with our time domain waveform, our time record of our signal being fed into the FFT. And what that will create is a waveform that looks like this. And this waveform here is our multiplied point by point, and to get the imaginary component, I'm going to take all of these values and I'm going to add them up. That will create the imaginary component. So between this and this, the sum of this, this creates the real part, this creates the imaginary part, and that creates the complex number, the single complex number that represents the value for that bin 1. As far as bin 2 is concerned, what we're going to be doing is we're coming back to our original waveform here. We're first going to multiply by 2 cycles of a cosine wave shown here, again on a point-by-point basis. That's going to make a waveform that will look like this, and this particular waveform again is 2 cycles. Just as I did before, once I've done the multiplication, I'm going to take all these 2048 points and I'm going to add them up. That will create the real part of bin number 2. The imaginary part, again, that is just the same as before. I'm going to take these 2 cycles of a negative sine wave, multiply it on a point-by-point basis. That gives me a waveform that looks like this. I'm once again going to take all of these values, I'm going to add them up, I'm going to sum them up. That creates the imaginary component for bin 2. And I'm going to keep doing this for every bin up until I get to essentially bin 2047, since this is 2048 points, but we start numbering at 0. Bin 0, that's the DC component again. We're just calculating the average effectively for that first bin, but all of the others will have a real part and an imaginary part, which you can also think of as having a magnitude and a phase. They're equivalent ways, just different ways to say the exact same thing. You can either think of it as real and imaginary, or magnitude and phase. Before I continue on, I want to be totally, absolutely, utterly clear here. The algorithm, the FFT algorithm, does not implement this as all of those multiplications, all the multiplications of x of n times the complex exponential, combined with all of those additions that we're talking about. If you do that, you're back to not the FFT, but the discrete Fourier transform, which is much more computationally intensive. It was actually because of that, because of this computational intensity, that they came up with the FFT. Looking at an article from Scientific American from 1967. Essentially, IBM ran, it looks like an article, but it's almost like an advertisement as well. And in this particular case, they're talking about the differences in the ability of the 2 algorithms, the original DFT, which required all of those multiplications and additions, versus how much more efficient the fast Fourier transform was. And when you look at this particular article for their testing, what they did was they chose a seismograph using 2048 points. So essentially exactly the same number as what I've been demonstrating here. And then they put that into both the original DFT algorithm and then a fast Fourier transform algorithm. And for the original DFT, it took almost 1,568 seconds to do that. If you do the math, that's somewhere between 15 and 20 minutes. Whereas with the FFT algorithm only took 2.4 seconds. So again, when you hear me talking about doing this correlation and all these multiplications and additions, I'm just talking about the general theory. I'm not talking about how the FFT actually works. Again, it's much more efficient than that, and it works. It doesn't do all of those adds and multiplications. It reduces all of, basically gets rid of all of the redundancy out of the system, and therefore it's much faster, as you can see here. And again, this is from almost 60 years ago, so even nowadays they're still even more efficient than they originally were. Continuing on. Coming back into our flow graph, we're going to go ahead and re-enable the various blocks, and we're just going to add another block in between the multiply constant and the vector to stream. Specifically, this will be the simply named FFT block. We're going to make a few adjustments to this though. First thing that we're going to adjust is the FFT size. We're going to change it from the default of 1024. We're going to say capital N to keep it with the same block size as everything else. The other thing that we're going to do is we've already windowed the data. We don't need this window part here. Instead, what we're going to do is we're going to use this to normalize the amplitudes of the output of the FFT. So I'm going to delete that, and I'm going to say left bracket 1 / capital N, comma, don't forget the comma, it's important, end bracket star, meaning multiply, capital N. So again, this is open bracket 1 / n, comma, close bracket, star, capital N. And again, only reason that we're doing that is that will then normalize the amplitudes at the output. I'm going to go ahead and click OK. Notice that now everything is happy. Let's see what the output looks like. And you might think, oh my gosh, I've lost all my data. No, you have not. Remember that we're now looking in the frequency domain, so the amplitudes are necessarily going to be fairly low. But if I put my cursor in the time domain display and just kind of roll the mouse wheel, do whatever you need to do to blow up the data, you notice that you're now starting to see, notice you got a signal here, matches this one here, I've got another one here, matches this one here. I'm even starting to see those digital shelves, the iBox on either side, as well as the analog portions, the analog signals. But again, remember, you're looking right now at this output here. You are looking at each one of these points is represented by a real and imaginary component, meaning it's represented by one complex number. And if I pause this, I can actually zoom in on each of these points and notice that there's this point here. This is the real part. This is the imaginary part. Real, imaginary. Real, the imaginary, the imaginary here, the real here. We can make it a little bit easier to see by going ahead and adding in markers. And so now notice that again, each one of these frequency bins is represented by a single complex value. And again, we can look at it as, yes, they are a real and imaginary, or we can also look at it as they are represented by equivalently a magnitude and a phase. So that's going to be important to understand for future videos. But again, remember, right now at the output of the FFT, I have created a display that each frequency bin still is in complex form and is represented by a real and imaginary, which can equivalently be thought of as having a magnitude and a phase. Okay, so we've now created this display, this FFT display, but it's not yet in a form similar to what we have down here. We're going to work on that next. Now that I have the output of the FFT, I want to put it into a form that we're more used to seeing with the vast majority of spectral displays. And to do that, again, I'm going to make a disconnect between the output of my FFT and my vector to stream, and I'm going to add in a block. known as the complex to mag squared. Again, the complex to mag squared. Now, if you have done any type of work with doing FFTs, you might have just said, well, could you also use the complex to mag? Yes, you can, but you don't want to, and there's a couple of reasons why. The first reason is that when you do the complex to mag, you're also having to take a square root. That's a very computationally intensive, processor-intensive process, so you don't want to have to do it. And ultimately it doesn't matter because you're ultimately going to want the square value, not the square root value. The other reason is that if I were to use the complex to mag and I try to average the data, it's going to come out wrong depending on where I put the averaging. It's either going to be 1 dB low or it's going to be 2.5 dB low, again, depending on where I put the averaging. So I want the complex to mag squared and not the complex to mag. All right, bringing this up, I'm going to change the value vector length to capital N. Now, notice that the output is a real only output. So I'm going to just make an adjustment to my other points here, and everything's happy now. Let's see what the result is. And you might think, oh my gosh, everything's really disappeared. Nope, it's just even lower now, amplitude-wise. So I'm just going to have to zoom in quite a bit in order to see our data here. And I'm going to just kind of zoom in on it. But notice it all kind of matches. This here, that was the ice in my cup. This here represents this signal here. This one represents this one here, here, and here. This one go to here, and this one, notice, is the lowest one down, so we're just starting to see it peak up. So we've now calculated effectively the magnitude, it's technically the magnitude squared, of each of the frequency bins. So we've gone from each one represents a complex value to just a real value, that real being the magnitude, and we have essentially thrown away the phase information, which is information typically doesn't tell us anything anyway, at least not in this context. We're getting down to the last few blocks here. The next block that we're going to add at the output of our complex to mag squared will be the one that will put the scale on a logarithmic scale, and that's specifically known as the log 10. This means you're going to be calculating the logarithm base 10 for each of these output values. And I'm just going to open this up and make two changes. One, instead of n of 1, I'm going to say n of 10, and then of course the vector length will be capital N, just like everything else. I now have everything the way I want it. Let's see what the result is. And notice that because our values, if our values are actually pretty close to what we're getting the frequency sync, and notice that the values here are between the actual values are between minus 30 and minus 110, minus 120. So I'm going to close this, going to come in here to our time sync, and I'm going to change our min to minus 120, and I'm going to change our max. You know what? I'm just going to make it equivalent to the frequency sync. So minus 140 on the low side and 10 on the high side. And let's see what it looks like. And notice that they now pretty much are equivalent. We have now built a basic spectral display. Now again, this is still in an oscilloscope, so it's not giving us our frequency scale, but the waveform looks pretty much the same. So the next part that we need to do is we need to make it where we can actually put a frequency scale on it so that it actually gives us values on the frequency domain that are meaningful to us. We're now set to add essentially the last block to this flow graph in order to make a fully functional spectral display, and that is the specific block that we're going to add is the Qt GUI vector sync, this block here. Now, what I've discovered through use of this particular block is it has a bug in the display, and just because of that particular bug, I'm going to add one more block, and that is a repeat block. And I'm just going to come in here, going to say float I'm going to adjust the various values. So I'm going to say float. I just need an interpolation of 2. That's enough to deal with the display issue. Set the vector length to n, and then I'm going to connect that to the output of our log10. Connect this to the input here of our QView vector sync. Now, the vector sync is going to require several different changes. First thing, vector size from 1024 default to capital N. The x-axis start value, well, our x-axis for pretty much all of our spectral displays here start at the negative half sample rate. So I'm going to say negative sample rate divided by 2. But that would mean that my scale is going to be in hertz. I'd prefer to either be kilohertz or in this case megahertz. So I'm going to, instead of saying /1e6, which would make it in megahertz, I'm just going to say divided by 2 million. So in other words, minus samp underscore rate /2e6. The x-axis step value is going to be similar. Our step value is just our frequency bin size. Our frequency bin size is our sample rate divided by the number of bins, which is capital N. But again, because we're operating in megahertz, I have to add another slash and then say 1e6, so that now it's in essentially step size of megahertz, which will be like point something something something. Our x-axis, instead of just calling it x-axis, we're going to say it is frequency, and I'm going to put in parentheses megahertz. And then our y-axis, we're going to say that is going to be amplitude dB. And I can just do the exact same thing, and this is for the cursor. So when you put the cursor on the display itself, it will actually give you, for the x-axis it will say it's in megahertz, on the y-axis it would say it's some dB value. Everything else we're going to go ahead and leave the same. I'm going to click OK, and I'm also going to go ahead and, for now, I'm just going to disable these 2 blocks. Reason being, I'm probably going to come back in and use the vector to stream. Running this, notice that we now have 2 displays and they look pretty much identical. The only way that you could really tell them apart is due to the fact that the QView vector sync has this for your legend, whereas for the frequency sync it just has this as the legend. But this is the one that we just made. This is the QGUI frequency sync. Try to tell them apart. You really can't. They are, for all intents and purposes, they are identical. So that is how we make a basic spectral display. Now, as I said before, we can keep the vector to stream. I'm going to go ahead and re-enable that. We're going to add a little extra touch to this, and that is I'm going to add in a time raster sync, and I'm going to turn that from byte into float. So if I open up, I started at byte, I'm going to change that to float. Going to keep the sample rate the same because that doesn't matter. Number of rows, keep that the same. The number of columns, however, I'm going to change to capital N. The other change that I'm going to make is the minimum. I'm going to set it -140, the maximum at 10. That means it's the equivalent, it's the same as the vector sync, as our frequency sync. Everything else I'm going to go ahead and leave the same. But I am going to come in here to configuration, and I'm just going to make sure that this says multicolor. That should be good. And I'm going to run this, and I now have not just a spectral display, but I also have a spectrogram to go along with it. So in other words, I've turned that time raster sync into a waterfall display. And there we are. This was just to create a basic spectral display. Future videos, I'm going to go into more depth on some minor tweaks that we want to do this to make it a bit more useful and usable. But in the meantime, I hope you appreciated this video, and I will see you on the next video.